we've seen that we can use algebraic limit laws to compute many kinds of limits. We're next going to look at another way we can find limits, and we'll use a result called the Squeeze Theorem. So with those algebraic limit laws, we weren't able to take any trig limits, for example, and some other kinds of limits we couldn't take. We're going to see that we can use the Squeeze Theorem to compute some trig limits. And at the end of week 3, we will see that we can extend the algebraic limit laws to many more kinds of functions. But here, we're going to talk about the Squeeze Theorem. So Squeeze Theorem, here is a partial statement of the theorem. Let f of x less than or equal to g of x less than or equal to h of x. Suppose, so we have 3 functions, one is less than the next. So suppose the limit as x approaches a of f of x, the smallest one, equals L. And suppose the limit as x approaches a of h of x, the biggest one, equals L. Then, well, what can we conclude? Well, let's call this an informal proof of the Squeeze Theorem. Well, let's draw f of x and h of x. Well, let's start with h of x, I guess. H of x could look something like that. All we know about h of x is that as x approaches a, h of x approaches L. Let's move a over a little. So that's at the bottom of this. So as x approaches a, h of x approaches L. It doesn't have to be defined at a, but it just has to, the limit as x approaches a of h of x is L. And f of x, we're supposing that that limit is L also. We're also supposing that f of x is always below or potentially equal to h of x. So here, f of x as x approaches a, the limit of f of x is L. And h of x is less than, or f of x is less than h of x, or equal to. Well, what can we conclude? Well, what do we know about g of x? All we know about g of x is that it's between f of x and h of x. Well, from that diagram, we see that the limit as x approaches a of g of x would also have to equal L. So we have 3 stacked functions, you can think of it like that. If what happens on the top is the same as what happens on the bottom in the limit, then what happens in the middle is also the same. And we're going to do 4 examples of this. 2 of them we're going to do algebraically. We're going to set up a Squeeze Theorem string of inequalities algebraically. And in the other 2, we're going to set them up geometrically, set it up geometrically. So first, let's compute this limit. Limit as x approaches 0 of x cosine x. Now, I know what you're thinking. You're thinking we can just do a substitution and get 0 times 1, and that equals 0. Well, we actually can't do that until the end of week 3. The algebraic limit laws do not tell us anything about trig functions. But what we can do now is use a Squeeze Theorem argument, because, let's observe, cosine of x is always between 1 and negative 1. The graph of cosine x looks like that, sort of. And it's always between 1 and negative 1. Well, that's great. That's not the function we want. The function we want is x cosine x. Well, if cosine x is between 1 and negative 1, how can we force x cosine x into existence here? Well, multiply everything by x. To multiply everything by x, you get x cosine x in the middle, you get negative x on the left, x on the right. And if the limit on the left, or the limit of the f of x as x approaches 0 is a number, and it's the same number on the other side, well, then we can conclude by Squeeze Theorem that the limit in the middle is that number. So we'll say, since limit as x approaches 0 on that side, that limit is 0 through a direct substitution or the limit laws, and the limit as x approaches 0 on this side, negative x, also equals 0. So the limit on the one side is 0, the limit on the other side is 0. We can conclude that the limit in the middle, again, as x approaches 0, is that same number by Squeeze Theorem. So we used property of cosine to set up our inequality, and then we forced the function we wanted to appear in the middle, and in doing that we were able to find the limits on both sides. The limits on both sides were the same, so the limit in the middle is also that same number. Let's look at one more. So limit as x approaches 0 of x cubed sine of 1 over x. Now, in this one, even at the end of week 3, when we have a substitution rule for trig functions, you can't do a substitution because you'd get 0 times sine of 1 over 0. Sine of 1 over 0 is undefined. So you won't be able to do a substitution here, but we can again set up a squeeze theorem argument because sine is also bounded by 1 and negative 1. Sine of 1 over x isn't defined at 0, but we don't care what happens at 0. It's defined everywhere else, so we can set up that inequality. Now, we want x cubed sine of 1 over x, so let's multiply everything by x cubed, as we did in the previous one with x. So multiply everything by x cubed, and now the function we want is in the middle. So if the limits on both sides of it are the same number, then the limit on the inside is that same number. So over there in the previous example, I wrote out since limit and limit equal whatever, we can conclude. Here I'm just going to say, I'm going to introduce a new notation. So an arrow going through it means taking the relevant limit. In this case, we want the limit as x approaches 0. So the limit of negative x cubed as x approaches 0, we'll just say equals 0 like that. And similarly over here, limit as x cubed approaches 0, or the limit of x cubed as x approaches 0 is also 0. Maybe I'll say, so we have that limit 0, we have this limit 0. So by Squeeze Theorem, limit as x approaches 0 of x cubed sine of 1 over x equals 0. So we had zeros on both sides in the inequality, in the limit. So by Squeeze Theorem, that limit is 0. So we can set up the Squeeze Theorem inequality we want using algebra sometimes. But we could also set it up using some geometry, using a graph. So let's look at 2 more examples where we use Squeeze Theorem to find some limits. So here, example, limit as x approaches 0 of sine of x. Now, again, we do not have a substitution rule for sine of x yet. But with a substitution, you would conclude it's 0. Instead of waiting till the end of week 3 to do this, let's find this limit using Squeeze Theorem now. And we're going to do that by considering a diagram. So here we have the unit circle. well, we have part of the unit circle. All we're going to need for this diagram is the first quadrant. So here, let's mark off some things in the unit circle. We have angle theta. Right here, this perpendicular, remember, the y-coordinate of this point is cosine theta sine theta. So this distance is sine of theta. Observation 1. Next observation. What is this distance? Well, we know this distance. The length of this arc. The length of that arc is defined, well, we defined the radian so that a radian measure was the length of that arc. So here, this angle measured in radians is the length of that arc, because this is the unit circle. You could alternatively use the radius times angle to get arc length. You could think of it like that. Radius is 1. But remember, we defined the radian so that it would be that arc length. Well, that diagram right there gives us all we need, because sine of theta, that perpendicular, well, that's larger than 0. But also, sine of theta is less than that curve. That curved piece, because this is the perpendicular going down, and this is a non-perpendicular going down. So from that diagram, sine of theta is between 0 and theta. Now we want to let, in this case, theta equal 0, or theta go to 0. So I'll just say, since limit as theta approaches 0 of theta equals 0, we conclude by Squeeze theorem that limit as theta approaches 0 of sine of theta. So the limit on this side, 0, doesn't change as theta goes to 0, so that limit's 0. Limit 0 here, limit 0 here, so the limit on the inside also equals 0. Now, yeah, in the statement I used x. And in the proof I used theta. Most of what we're going to be doing, our input for our trig functions, will be just x. But in doing a diagram with an actual angle, I like using theta. So to go from this observation to this, just replace theta with x. Or in the diagram, you could have labeled the angle with x, but I always like labeling angles with thetas. Well, we have that this limit now equals 0. We can use that to find some other limits, using the algebraic limit laws. For example, limit as x approaches 0 of cosine of x. Well, what does that equal? It equals that. Why does it equal that? Well, remember, sine squared plus cosine squared equals 1. So cosine squared is 1 minus sine squared. So cosine is root 1 minus sine squared. Well, how can we compute this limit? Well, we can compute this limit using the algebraic limit laws, because we have a function to the 1/2. So we have a function to the 1/2. Then we have a sum, the difference of sum. Then we have a constant, a function squared. So we can use rules 7 to push it inside the 1/2. We can use rule 3 to split it into the limit of the sum. We can then use rule 7, well, we can then use rule 1 to take the limit of 1. We can then use rule 7 to push it inside this squared function. And that gets us to that this limit equals this limit. So using those 3 rules, using rule 7 twice, we have that that limit equals this limit. And can we compute this limit? Well, yes, we can, because of that example. that example says that this limit inside here is 0. So we get 1 minus 0 squared. So the limit as x approaches 0 of cosine x is 1. Well, we have sine and cosine now. Well, we can also do tangent of x. Limit as x approaches 0 of tangent of x. Well, tangent of x, remember, is just sine of x over cosine of x. And we have the result for sine and cosine. So we can compute this limit using algebraic limit rule 6. We can push the limit into each piece of the quotient. And then we can compute both limits by the previous two examples. The limit on top is 0, the limit on the bottom is 1, and 0 over 1 equals 0. So these last two examples didn't use the Squeeze theorem directly. They did technically use Squeeze theorem in evaluating the sign limits. But the work for that was all the way over here. Those largely followed from algebraic limit laws. So now, let's do one more example using a diagram. So we're going to show limit as x approaches 0 of sine x over x. We're going to show that this limit equals 1. Well, how are we going to do this? Well, I'm going to draw it on the third board, actually. So let's again draw a unit circle, or a piece of the unit circle. So here's a piece of the unit circle. Let's again mark off that distance. This arc, again, has length theta. This distance here, again, that's perpendicular. This distance, again, let's mark that angle as theta. This distance is sine of theta, but let's also mark a couple more things off on this. This distance, remember the coordinates of this point are cosine theta, sine theta, so this x-axis distance is cosine theta. And we're going to mark off one more distance here. So we're going to extend that out, and we're going to drop a perpendicular down. And we're going to concern ourselves with this distance. We don't know what it is yet. Let's call it box. That box, B-O-X. So here we have that distance and all these other distances marked off. Let's call this unit circle. T circle. So unit circle, the radius is 1, which we'll see in a moment. But with all of these things labeled, we can figure out what box is by observing similar triangles. Which triangles? I don't see triangles. Well, maybe I do. Let's make it more clear where the triangles are. So we have triangles like this, where this length is box. This big triangle is similar to this smaller triangle by what? Angle, 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 because those are both right angles at the bottom. So this distance here is cosine theta. This distance here is sine of theta. That distance is box. So we can set up a ratio. Using the small triangle, let's do this side over that side. On the small triangle, we have sine theta over cosine theta. The corresponding sides in the big triangle are box over this entire distance. What is that entire distance? Well, let's look up here. What is this distance? Well, that distance is just the radius of the unit circle. So that distance is 1. So simplifying this, we find that box equals tangent of theta. So in this diagram, It's supposed to be like a straight line going out. In this diagram, that box is tangent of theta. Now, how is that going to help us? Well, we can set up a squeeze theorem inequality by looking at this length, and this length. So observe. What are we observing? Sine of theta is less than or equal to theta is less than or equal to tangent theta. So this straight line is less than that curve, and that's less than or equal to, in the limit it will be equal, less than that box distance, which is tangent of theta. Well, this isn't what we want. We want sine of x over x, sine of theta over theta. And we want that in the middle. How can we force that into existence? Well, we can start by dividing everything by sine of theta. What happens if we divide everything by sine of theta? Well, over here, so dividing by sine theta, we have what? 1 on this side. Sine theta divided by itself is 1. Less than or equal to theta over sine of theta. So divide that by sine theta, we have theta over sine theta. Almost what we want, not exactly. And what do we get over here? Well, over here we have tangent of theta divided by sine of theta. Well, tangent of theta is sine over cosine. So we have sine over cosine over sine. Sine over cosine over sine is multiplied by the reciprocal. Sine over cosine times 1 over sine. So that's just 1 over cosine. So tangent theta divided by sine theta is 1 over cosine of theta. Well, I'm going to go over here now to finish this. Well, that's not exactly what we want. We want sine theta over theta, not theta over sine theta. So let's just flip everything around. So taking reciprocals, what do we get? Well, reciprocal of 1 is 1. When you take the reciprocal of an inequality, you have to flip everything, the inequalities around as well. Because what? 3 is greater than 2, but 1/3 is less than 2, for example. So take reciprocals, or 1/3 is less than 1/2. So take reciprocals of everything, you get 1 greater than or equal to sine theta over theta, greater than or equal to cosine theta. Well, that doesn't look exactly like our squeeze theorem things. So let's just rearrange. We have, just write it backwards so that it's in the exact form of the squeeze theorem if you want. That's a 1. So just rewriting it backwards, you have cosine of theta less than or equal to sine theta over theta less than or equal to 1. And we still haven't proved what we want, but since the limit from our fourth example today, the limit as theta approaches 0 of cosine theta equals 1. So the limit over here is 1. The limit over there is also 1. By squeeze theorem, well, maybe that's misplaced. So since that limit is 1, we conclude limit as theta approaches 0 of sine theta over theta equals 1 as well by squeeze theorem. Theorem, THM, that's okay. So we proved that for theta. So for this actual statement, let theta equal x. So these squeeze theorem arguments, they could require a diagram. I'm going to see if I can find another one that requires a diagram. I couldn't find one last semester or the winter, but I'd like to put one that has some algebra in it, like the first 2 examples we did, and I'd like to find one that also uses a similar diagram. I'd like to put that on the worksheet. Maybe not a test, but the worksheet definitely. I'd like to see if I can find one. But setting up the squeeze theorem inequality does take a good deal of practice and I mean, I always find that these take a little more patience to set up than the other limits we do.